think we left off last time in this slide where we had the mean, variance, and standard deviation for just a data set. When we convert these into dealing with a probability distribution, the mean is just the expectation, which is the sum of the outcome times the probability of that outcome. The variance is the sum of the outcome minus its expectation. Remember, this mu is expectation times its probability. And standard deviation is still the square root of the variance. So let's look at a couple of examples. So let's use the same probability model that we looked at before. Here the expectation we calculated was 1/2. So to calculate our variance, we're going to take 0 minus the expectation, 1 minus the expectation, 2 minus the expectation, and so on. That's going to give us this part. Then we're going to square them. So negative 1/2 squared is 1/4, 1/2 squared is 1/4, and on. And then times the probability, so 1/4 times 125 over 126 is 125 over 864. And then 1/4 times 25 over 72, and so on. And then we're going to add these all up. When we do that, we get 5/12. So that's our variance. And our standard deviation then would be the square root of that, which is about 0.645. So again, we just took the square root of 5/12. Let's do another. So here we have a new probability model. So this is the number of laptops sold in a day, and this is the probability of that outcome. So again, the expectation, the expected value, is just the sum of the outcome times its probability. So 0 times 0.08, 1 times 0.4, 2 times 0.24, and just going to add those all up. When we do that, I get 1.9. That means we expect to sell 1.9 laptops each day. Now, if I want the standard deviation, here's my expectation. So I'm going to have 0 minus 1.9, 1 minus 1.9, 2 minus 1.9, and so on. And then I'm going to square each one of these, so negative 1.9 squared, negative 0.9 squared, and so on. And then I'm going to multiply these by the probability, so 0.8 times 3.61, 0.4 times 0.81, and so on to get these. I'm then going to add this column up, so 0.2888 plus 0.324 plus 0.0024, and so on, to get me 1.63. That's my variance. To get my standard deviation, then I take the square root of that, and I get about 1.28. So again, variance was the same as standard deviation squared, 1.63, or the standard deviation is 1.28. So this means on a given day, there'll be the number of laptops sold on average will be 1.28 laptops away from the expected or mean number of laptops sold, which is 1.9, which is a pretty big variance, right? Because that's, almost the size of the mean. Okay. If we want a more effective way of calculating the standard deviation, we can use our calculator and kind of bypass these lists that we've been making. So what I can do is I can just enter my outcomes into L1 and my probabilities into L2. Then I can do a one variable stats with L1, but for the frequency list I need to use L2, and then hit calculate. That's my standard deviation. Much easier than making the lists like we just did before. Okay, so the key thing to remember though is that the outcomes are in L1, the probabilities in L2, and when you do your one variable stats, you have to set up a frequency list. Remember, to get the L1, L2, L3, L4, press second and the number sign on your calculator. So second and the number 2 will give you the L2 on your calculator. Take a minute and try typing this into your calculator on your own and making sure you can get that. Pause your video or whatever. Let's do another. So let's say we want a data set and we want to convert this to a probability model. So we have the number of persons and then the number of households in millions. So there's 31.1 million one-person households, 38.6 million two-person households, and so on. So the first thing I want to do is I want to convert this number of persons into outcomes, and I want to convert this number of households into a probability. Well, the only issue with the outcomes is this 7 or more category. We're just going to call that 7 or more just 7. Okay? So we'll just call that exactly 7. So if we do that, this column just becomes our outcomes column, our X. And then to convert these into probabilities, I'm just going to take the number of outcomes of that type, so 31.1, and divide it by 116. And that gives me something like 0.268. And I'll do that for each column. And now I have a probability model because I noticed that I have discrete number of outcomes and the probability of each outcome adds to 100% or to 1. So find the probability that a person randomly chosen from a randomly chosen household has 4 or more persons. So 4 or more means you could have 4 people, 5 people, 6 people, or 7 people. So I'm going to do the probability of 4 plus the probability of 5 plus the probability of 6 plus the probability of 7. Again, these are mutually exclusive because an exactly 5-person household can't have 4 people in it or 6 people or 7, right? Because we changed these to be exactly. They're now mutually exclusive, meaning that there's no overlap. So I just now add the probabilities to get 0.237. If I want the expected value, remember that is the outcome times its probability, and we add up all the possible outcomes times their probabilities. So 1 times 0.268 plus 2 times 0.33, and so on. And we get there 2.512. And now, again, there's an easier way to do this than just typing our list in, although this is perfectly effective. Let's show you the shortcut to do this on our calculator. So what I'm going to do is I'm going to type in, this is my L1 and this is my L2. And I'm going to go to one variable stats, run variable stats with L1 as my outcomes and L2 as my frequency list. That should be my probabilities. Make sure it's the probabilities and not the counts that we had earlier. We need to have a probability model when we do this. So that conversion to probability model needed to happen before I did this step. But now I just run my one variable stats and I notice that the mean and the sum are the same, which should be the case if we have a probability model. So we got the same value, right? That was a little bit quicker. Again, if these two are not the same and you're using a probability model, it means that you have made a typo because those two numbers should be the same. The mean and the sum of the x's. Because remember, when we put a frequency list, it's going to be this number times this number plus this number times this number, and that's going to be the sum. And the reason the mean is the same as the sum is because we're dividing by 1. because that's the frequency list. So if I divide the sum of these things by 1, I still get the same thing. So that's why the mean and the sum are still the same. But that's your cue when you're looking at the one variable stats to know you've done this correctly. So if I want the standard deviation, again, I'm going to use my calculator. Since I already have the stuff in L1 and L2, I can, again, just look at my one variable stats, which I already had up, and the standard deviation is just my standard deviation. Let's do one last example. So let's say we wanted to create a probability distribution for the discrete random variable x that counts the number of heads in 4 flips of a fair coin. So we're flipping a coin 4 times. I'm going to draw a tree diagram to help me keep track of all the possible outcomes. So my first flip, I can get heads or tails. After the first flip, if I have heads, I could again get heads or tails, and if I got tails, again I could get heads or tails. And I'll do a second flip or a third flip for all 3 of these, or I'm sorry, all 4 of these. And that gets me this, and then I'll do my fourth toss. And so these are my outcomes. Heads, 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 tails, and so on. So these are my outcomes. So I have, if my variable is for the number of heads, there are 5 possible outcomes. I can get 4 heads, 3 heads, 2 heads, 1 head, or 0 heads. And since this is a fair coin, that means each outcome is independent and equally likely. So every outcome has a probability of 1/2, right? There's a 1/2 on each of these, and a 1/2 on each of those, and a 1/2 on each of those, and a 1/2 on each of those. So every place, every branch of our tree is a 1/2 probability. So any path I do is going to be 1/2 times 1/2 times 1/2 times 1/2, or 1/16 or 0.0625. So every one of these outcomes has the same probability. Now, if I look for the x, the number of outcomes, so how many outcomes give me 0 heads? If I look through here, only 1. So the probability there is just going to be the probability of 1 outcome, so it's 1/16 or 0.0625. Then I'm going to look for the number of outcomes that have 1 head. So there is 1 head, 1 head, 1 head. I think I missed one in there. Yeah, there we go. There's 4 of them. So I'm going to have 0.0625 plus 0.0265 plus 0.0265 plus 0.0265, or that turns out to be 0.25. I'm going to look for the 2 outcomes, or where I have 2 heads. So 1, 2, 3, 4, 5. Nope, there's a 6th one there somewhere I missed. I don't know where it was. Anyways, 6 of them. So again, 0.0265 plus 0.0265 plus 0.0265 plus 0.0625 plus 0.0625 plus 0.0625. Gives me 0.375. Now I look for 3 heads. 1, 2, 3, 4 of those. So again, that was 0.25, the same thing as 1, because there were 4 ways to get 1 head. And then look for 5 or 4 heads. There's only 1 way to do that, and so that is just 0.0625 by itself. So here's our probability distribution. That took a little bit of effort because we had to draw out and figure out how many outcomes of each were possible and figure out the probability of each of those outcomes. But that's it. At this point, you guys should work on the in-class example problems from Chapter 12. So run through and try to do those. And then you can work on the 12.1 problems from the textbook. And I'll get that up into Miner Dame here in a few minutes. Okay? Have a good day. Bye.